Hey guys, moving on to 3.2 today. So today we're going to write and evaluate linear functions using function notation. Okay, we're going to graph some again and talk about the domain. And then we're going to interpret functions represented by graphs, tables, verbal descriptions, and function notation. Okay, so this is 3-2 linear functions. So we're going to start right off with function notation. Okay, so like I've said before, this book likes to drop us right into a problem and then tell us about the notes. So we're going to, how can we represent a function rule? So we're going to write the equation y equals 5x plus 1 using function notation. Remember that a function is a rule that takes an input or an element in the domain and maps it to an output, which is an element in the range. Okay, so a lot of books like to represent function notation as a function machine. Okay, we put this input in, goes through the machine, so it goes through the rule, and then it comes out the output. So function notation is a method for writing variables as a function of other variables. Okay, so this is saying the variable y becomes a function of x. Okay, meaning y depends on what x is. Okay, which means the variable x is used to find the value of y. This helps distinguish between different functions, and the relationship between the variables can be used to solve problems and make predictions. Okay, sometimes we have to have like 3 equations to describe a situation. It's really confusing if we call them all y equals, and y equals. So we use function notation. Okay, so function notation is just simply replacing y equals with f of x equals. Okay, so f of x is the same thing as y. Okay, it's saying it's a function of x. So the function f is defined in function notation by f of x equals 5x plus 1. Okay, so it's saying x is what our function depends on. Okay, so x comes in, goes through the rule, f of x comes out. Okay, so here's how we actually use function notation. So what is the value of g of x equal to 5x plus 1 when x equals 3? Okay, so this time they're giving us what the input is. So we're going to throw 3 into our machine, substitute anywhere we see an x, we're going to plug in 3, and solve for what g of x equals. Okay, g of x is what comes out. Okay, so this is my input, and I replace it anywhere I see an x. So I'm going to say, instead of 5x plus 1, I'm going to say 5 times 3 plus 1. So what is 5 times 3? 15 plus 1 gives me 16. So my output is 16. Okay, so g of x equals 5x plus 1, and then g of 3 is equal to 16. Okay, g of 3 means the value of the function g when x equals 3. Okay, so you can think of this as an ordered pair. X is 3, and what we get out, the 16, is my y value. So all you're going to do is evaluate each function. Okay, so pause the video and try letter A, please. Okay, g of x equals negative 2x minus 3. Okay, I know x equals 4. So anywhere I see x, I'm plugging in 4. So g of 4 is equal to negative 2. Instead of writing x, I'm going to write 4 minus 3. So g of 4 equals negative 2 times 4 is negative 8 minus 3 equals negative 11. Okay, so negative 11 is my answer. Okay, pause the video, try letter B. Okay, again, remember you're using x equals 4. So h of x equals 7x plus 15. We want to find h of 4. So again, anywhere I see an x, I'm stuffing in 4. So 7 instead of x, I write 4 plus 15. So h of 4 equals 7 times 4 is 28 plus 15. So h of 4 equals, let's see, 43. And there's your answer. Okay, moving on to example 2. We're going to write a linear function rule. So the cost to make 4 bracelets is shown in the table. How can we determine the cost to make any number of bracelets? Okay, so I see 1 bracelet costs me 17 to make, 2, 32, 3, 47, 4, 62. So the first thing we want to do is examine the relationship. Do we have a linear relationship? Well, if I call this x and this y, I do my linear loops, you see these are all increasing by 1 each time. How much am I increasing here? Well, 17 to 32 is plus 15. 32 to 47, plus 15. 47 to 62, plus 15. So it looks like I have a linear relationship. Okay? Because I have a linear relationship, I can use y equals mx plus b. So we're going to write the function using slope-intercept form. Okay? So I need to figure out two things, the slope and the y-intercept. Okay, remember slope, which is y2 minus y1 over x2 minus x1. But guess what? You have already done that. Okay, remember slope is the same thing as the change in y over the change in x. Right here is your change in y. Okay, see how every y changed by 15? Right here is your change in x. So my slope is just 15. So I already know what m is. Oh, that was pretty easy. Okay, now I just gotta find b. So I can pick any ordered pair from the table and plug it in. Okay, ooh, I like this pair right here. 1 is easy. So let's plug in x, y, and m. So instead of writing y, I'm gonna write 17. M, that's the 15 we found over here. X is 1 plus b. So first thing I should do is multiply 15 times 1, which is just 15. How do I get b alone? Subtract 15. So 2 equals b. Last step, let's write the equation. So y equals 15x plus 2. That is my function rule. Now, if I wanted to, I could also write this in function notation. Remember, instead of writing y equals, I just write f of x equals. So f of x equals 15x plus 2. And there you have it. All you need to do. Okay, your turn. Pause the video and try letter A. You're going to write a linear function for the data in each table using function notation. Okay, so the first thing I'm going to do is find my linear loops. Okay, looks like I'm just going up by 1 each time. Okay, here, 6.5 to 13 is 6.5. Plus 6.5 again. And again. So, this is linear. I can use y equals mx plus b. Okay, remember, m is your change in y over your change in x. So here's my change in y over my change in x, which is just 6.5. Okay, pick a point. I like this one. I like 1. It makes it easy. And let's plug and chug. So my y is 6.5. M is 6.5. X is 1. And we don't know b. Okay, so 6.5 equals 6.5 times 1, which is 6.5. Subtract to get b by itself. 0 equals b. So my equation here is just y equals 6.5 x. You could write plus 0 if you wanted to, but you don't have to. And there's your answer. Your turn again to pause the video and try letter B. Okay, first thing I'm going to do again is find my linear loops. 1, 1, 1. Okay, down here, plus 3, plus 3, plus 3. Okay, so I can already tell my slope is equal to change in y over my change in x, or just 3. Okay, so if I do y equals mx plus b, excuse me. Okay, again, I like easy points. We're going to use 1, 1. So y is 1, m is 3, x is also 1, plus b. Okay, so multiply. 3 times 1 is just 3. Get b by itself, we're going to subtract 3. So negative 2 equals b. Last step, write the equation. Y equals 3x minus 2. And there we have it. Right. Let's analyze a linear function next. Okay, so Tamika is recording the outside temperature at 6 a.m. The temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 o'clock p.m.? Okay, so the first thing we need to do is write a function. Okay, so function I know is y equals mx plus b. Okay, so, does it look like I have a point? No, it does not. So when that happens, you got to ask yourself, okay, do I have the slope and the y-intercept? Do I have the slope and a point? Do I have 2 points? What's going on here? Well, remember, slope is the same thing as your average rate of change. Okay, I'm increasing by 2 degrees Fahrenheit every hour. That right there is your slope. Okay, my slope is increasing by 2. Okay, so m equals 2. Okay, my y-intercept, remember, is your starting point. If you look at the picture right here, that's what the temperature is starting at. So that is my b value. So my equation is just y equals 2x minus 3. Okay, so that's my equation. Okay, so then it says suggest sketching a graph. Okay, we've graphed a slope-intercept form a lot. Okay, you start at your y-intercept and then you use your slope. So my graph looks like this. Okay, so the graph of y equals 2x minus 3 is a line. A linear function is a function whose graph is a line. Okay, everything we've talked about so far has been linear. Later this year, we're going to get into nonlinear functions. We're going to look at exponential functions and quadratic functions. Okay, so those are not going to make a straight line. Okay, but if it makes a straight line, it is linear. Okay, so that can help us kind of see it. Okay, but has that answered the question? The question says, what will the temperature be at 2 o'clock p.m.? Well, I've got this equation, I've got this graph. Does that help me get to 2 p.m.? Well, let's read what the problem said. Okay, we know the temperature is increasing every hour. Does 2 o'clock tell us how many hours has passed? No. So we need to figure out from our starting time how many hours passes till we get to 2. That will be the x value we plug into our equation. So if I start at 6 a.m. and I want to go to 2 p.m., that is 8 hours. Okay, think about it. 6 a.m. to noon is 6 hours. And then go to 2 is another 2. So a total of 8 hours. So in order to solve this problem, we need to plug in 8 for x. Okay, so we're going to plug in 8. So y equals 2 times 8 minus 3. Y equals 16 minus 3. Y equals 13. So if this trend continues, the temperature will be 13 degrees Fahrenheit at 2 o'clock p.m. Okay, and we have solved that problem. Right, so here's another question to think about. Does using a linear function realistically represent temperature for the domain of 0 to 24? Why or why not? Okay, well, let's think about it. The domain was the number of hours that had passed. Okay, so does this linear function really realistically represent the temperature for a full day? What do you think? Well, okay, so the graph has a slope of 2, which represents the temperature rising 2 degrees every hour. However, when the sun sets, is my temperature still going to continue to rise? Absolutely not. Okay, when the sun goes down, we know it gets colder outside. Okay, so this linear function is not realistic for the whole day. It's realistic only for a portion of the day. All right. For 3A and 3B, all you need to do here is sketch a graph. Okay, so let's do 3. Pause the video and try. Okay, so remember the first thing we need to do is find our slope and our y-intercept. Remember, this is your y-intercept, and your number in front of the x is your slope. So my y-intercept is 1, so I'm going to start there. Okay, my slope is negative. Remember, you can always make it a 1 there. So that means -1, put it over 1, goes down 1, right 1. Okay, so down 1, right 1, down 1, right 1. Okay, over and over again. Get tired of that, you go up 1, left 1, up 1, left 1. And that is what your graph should look like. Please pause the video and try letter B. Okay, so same thing. My y-intercept is 1, slope is 3, so I'm going to go up 3 over 1. 1, 2, 3. Out of room, so down 1, 2, 3, and left. And that is what your graph should look like. Okay, example 4, moving on. We're going to solve a problem with a linear function. So a chairlift starts half a mile above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? Okay, so we need to write a linear function to represent the distance the chairlift travels from the base of the mountain. Okay, we're half a mile from the base to start off, and we know it's traveling at 6 miles per hour. Okay, so we're going to let t equal time in minutes. Unfortunately, they give us the time, excuse me, the rate in miles per hour. So we need to convert the speed to miles per minute because we're working with minutes. Okay, so 6 miles per hour. And I want to get it to miles per minute. Okay, so you got to think all the way back to 7th grade here. We need to do some conversions. So I can keep the miles the same. I need to convert the hours to minutes. So we're going to use some dimensional analysis here. Do we know anything about hours and minutes? Well, there's 60 minutes in 1 hour. So I need to figure out, do I put the minutes on top or the hours on top? Well, when I multiply, remember you can cross cancel. So if I have hours on the bottom, I want to cancel the hours out. So I need to put the 1 hour up top. Now 1 hour, we just said, is the same thing as 60 minutes. So 60 minutes goes on the bottom. Okay, so from here, notice, oh look, the units cancel. So this is really just 6 over 60, which reduces to 1. Okay, so this means it moves 1 mile every 10 minutes. So this is my slope. Okay, so we're going to write the equation now. So y equals 1/10 x. Where did I start with my distance? Well, that's just 0.5. Okay, so plus 0.5. Okay. So now we want to answer the question. The question says, how far is the base of the from the base of the mountain is the chairlift after 10 minutes? So now I have my equation. I can just plug in time of 10. So y equals 1/10. Instead of writing x, I'm going to plug in my 10 there, plus 5. Nice thing about the fractions here, 10 and the 10 cancel. So y equals 1 plus 0.5. So y equals 1.5. Okay, the chairlift is 1.5 miles from the base after 10 minutes. And there's the answer to the problem. All right, so your turn. A chairlift starts half a mile above the base of the mountain and travels up the mountain at a constant speed of 6 miles per hour. How would the function, graph, and equation change if the speed is 4 miles per hour? What's the effect on the domain? Okay, pause the video and see what you can come up with. Okay, so looking at this, I needed to know, I know my slope is going to be different. Okay, I had to convert the 6 miles per hour to miles per minute. So we're going to do the same thing with 4 miles per hour. Okay, so remember we had 1 hour for 60 minutes. Okay, and that's going to equal 4 over 60, which reduces to 1 over 15. Okay, so my equation changes to 1/15 x plus 0.5. Okay, so my slope changed. Okay, I'm moving slower, so my slope is less steep. Okay, so the starting point is still the same. My y-intercept didn't change. Okay, so then my domain would then be increased because I need more time. All right, so that's what this lesson's about. Okay, so remember, big thing with function notation is we use f of x. Okay, it tells us it's a function and x is our input. Okay, and then tables and graphs we've worked with a lot. So the newest thing here was f of x. So here's your homework. Please come prepared with any questions you may have. Hope you guys have a nice day.